Hello, everyone. Welcome to this week's current seminar. Today we have one speaker. The speaker is Dr. Albert, who's a postdoctoral researcher in the School of Mechanical Engineering at Purdue University, where he also earned his PhD in 2024. Before joining Purdue in 2019, he earned both a Bachelor in Science and a Master in Science in Applied Mathematics at the University of Akron. His research is focused primarily on techniques for inverse problems and scientific machine learning. Alex, thank you so much for joining us today. And with this short introduction, you can start whenever you're ready.
Great. Thank you for inviting me to come here today to give a talk. Today, I'm going to tell you about information field theory, which is my approach for solving infinite dimensional Bayesian inverse problems. And the mathematics of IFT is what really I'll dive into today, is based on the theory of path integrals that you may have seen if you've studied a little bit of quantum physics. So first, to give some background about me, is I did earn a bachelor's and master's in applied mathematics at the University of Akron. So I worked with Patrick Wilbur and Dane Quinn. I was co-advised, one for math, one for mechanical engineering. And what my thesis was on was some asymptotics, where I was looking for Fano resonances in Duffling oscillators. So you have these strange resonance conditions where you have an anti-resonance, which is when the steady state response hits zero right next to your resonance condition. So then I went on to do my PhD in mechanical engineering at Purdue, where I worked with Ilias Bilionis, and I spent the larger part of my PhD actually developing information field theory and how it can be applied to engineering problems. And now I stayed as a postdoc at Purdue, and I primarily study inverse problems, uncertainty quantification, and sort of tangentially mathematical physics. So information field theory, or IFT, is just Bayesian inference for fields which relies on path integrals. So IFT was largely developed by Torsten Enslin of the Max Planck Institute for Astrophysics, where they developed and used IFT for solving these sort of field reconstruction problems with data coming from satellites, where they want to understand different properties of the universe, such as the gamma ray radiation and this sort of thing. So this concept of using path integrals for Bayesian inference actually predates Enslin. There's a book called Bayesian Field Theory, which was developed, I think, 10 years before he started working on this, where they were using the same idea. So why we care about using these path integrals for Bayesian inference is that IFT gives us a very nice natural method for working with non-Gaussian random fields. So in engineering applications, we study a lot of fields which appear in non-Gaussian ways. And when you're doing Bayesian inference, your prior matters. It is very important that you have a good prior. So if you have some material which has this sort of shard, looks like shards, then you cannot capture this with the Gaussian process prior, and you need something that's non-Gaussian. So how IFT works is we want to define these prior probability measures over function space using formal Lebesgue densities. And what I'm really interested in is defining these priors in a way that respect physics, so that we have physics-constrained priors. So before I get into IFT, I need to talk about, go through a bit of background and settings. So I'll talk about inverse problems, kernel methods, Gaussian processes. So looking at solving inverse problems, if you take the standard definition of an inverse problem, you have some data coming from an underlying field of interest U, which lives in a Hilbert space, and then you apply some measurement operator to it. And the measurement operator R is in general nonlinear, and then of course you have some observational noise. And then the goal is to just invert the data, invert the map between the data in the hidden state. So you're given the data and you want to uncover this underlying field U. So inverse problems cover many, many problems in science and engineering. Of course, it's one of the largest fields of applied mathematics today. So the first method to go over is kernel methods. So this is a well-established regression technique that works in the theory of reproducing kernel Hilbert spaces. And they have a very deep connection to Gaussian processes. So what a reproducing kernel Hilbert space is a Hilbert space with equipped with an inner product such that your reproducing kernel K lives in this Hilbert space, and the kernel possesses this property known as the reproducing property, where you can write every single element of the RKHS as this inner product against the kernel under the kernel space inner product. So we use the theory of reproducing kernel Hilbert spaces to do a technique known as kernel ridge regression, where we want to solve the following problem, where we take our training data from before and we try to minimize the fit between our training data and our function representation. So we represent it in the reproducing kernel Hilbert space. And then we add this additional term, which actually serves as a regularizer, because it's known that as a function has a smaller reproducing kernel Hilbert space norm, it's actually smoother. So you are simultaneously encouraging your representation to fit the data that you have while smoothing your fit so that you don't overfit. And kernel ridge regression has a known solution, which looks like this, where you build this matrix capital K, which is built from the pairwise correlations between your data points. So we all know and love Gaussian process regression, where you start with, you represent your field that you're trying to identify as a Gaussian process, and then you take your training data and you condition your Gaussian process on your training data to derive your posterior, which is also a Gaussian process in this case. So we know what the mean function and the covariance function of the posterior Gaussian process looks like. And you'll notice that we see this form that showed up in kernel ridge regression. It appears again, and it turns out that there's an equivalence between the two, in that Gaussian process regression can be viewed as the Bayesian interpretation of kernel ridge regression. This is because their solutions are actually equivalent under some mild assumptions, namely that if you take the same kernel and you take your same training data, and you do kernel ridge regression with that kernel, and you do Gaussian process regression where your prior has this kernel, if you select the learning rate in the regression to be to match the noise in your data, then the posterior mean function resulting from your Gaussian process regression will be exactly the unique kernel ridge regression solution. So in this way, we can view the kernel ridge regression solution as the map estimate of Gaussian process regression. And then later on, I'm going to build a similar connection between IFT and physics-informed neural networks. So continuing with background, now I want to talk about infinite dimensional Bayesian inverse problems, sort of in the sense of Andrew Stewart's work from 15 years ago. And to do this, we need to also understand how Gaussian measures on Hilbert spaces work. So in finite dimensions, your Bayesian inverse problems are quite easy to solve, where you can just apply Bayes rules. So theta is some random vector of interest, some parameters that you're trying to fit. And then you write down your likelihood, which describes your physical model. And then Bayes rule just gives you the posterior, and then you can characterize it through a number of ways, usually with some sort of Monte Carlo scheme. Now, Bayesian inverse problems in Hilbert spaces, so infinite dimensional function spaces, usually involve Gaussian measures on those Hilbert spaces in some way. And we say that a measure on a Hilbert space is Gaussian if its projections are normally distributed. And in this case, we write it's how you would see a normal Gaussian measure, but now this C is some covariance operator. So it's an operator from your Hilbert space onto itself. And this covariance operator needs to satisfy some conditions in order to have a valid Gaussian measure. namely that it needs to be positive, definite, symmetric, and also trace class, which means, so this means that it has a finite trace. And it's often easiest to characterize these Gaussian measures by their characteristic functionals. So if you start with a Gaussian measure, its characteristic functional looks like this, which is just the Fourier transform of the measure. And the reverse also holds, that if you end up with a functional that has this sort of form, then it's the characteristic functional of some Gaussian measure on that space. So there's a strong relationship between Gaussian measures and Gaussian processes, but it's not always one-to-one, namely that Gaussian processes don't always correspond to some Gaussian measure. So we have this result between the two that says if you start with a Gaussian process which is measurable, then your sample paths belong to L2 if and only if you can take your mean function belongs to L2. And also your kernel of your Gaussian process satisfies this condition. And if the above holds, then your Gaussian process induces a Gaussian measure on the same on L2, where the covariance operator of the Gaussian measure is just the integral operator with the kernel coming from your Gaussian process. Now, the reason that they're different is that this trace class condition is often violated. So, for example, if you start with the white noise kernel, then this condition will be violated on R, and you no longer have a trace class covariance operator, so you can't define a Gaussian measure. So they're not always equivalent. It's something to keep in mind for later.
Alex, can I ask a question here? Because it seems that in all physical processes, these conditions are satisfied, right? I mean, it means that you just said it, that you should not make a white noise assumptions.
Yes, so later I will actually show you that for the Brownian bridge, this condition is violated whenever you go beyond one dimension. And the reason this is important is I will show that if you start with the Poisson equation, then the Brownian bridge is the correct prior to put on the Poisson equation.
I see. Okay. All right. Thanks.
Yes. All right, continuing forward with solving inverse problems in infinite dimensions is that we can't just apply Bayes' rule in the usual way that we like to think. So if you start with some target function in your Hilbert space that you want to fit, and then you collect some data coming from it, then Bayes' rule takes on this sort of form, where we describe the posterior using the Radon-Nikodym derivative between your posterior measure and your prior measure. So here, this derivative is actually the form of the likelihood. And this is how we describe the posterior or Bayes' theorem in infinite dimensions. So it's quite difficult. And then the important condition here is that you need the domain of your measurement operator to have full measure under your Gaussian prior. And this has some issues that we'll talk about in a little bit. So the way that we add physics to this paradigm of solving inverse problems is that you have some field that you're trying to identify, and you start with a Gaussian prior over it, so you fit a Gaussian measure to it. And then you put the physics into the likelihood. So if you have some PDE where the field you're trying to identify is a coefficient, like a spatially varying coefficient of the PDE, then you describe your measurement operator as the solution of the PDE at some collocation points at the current value of your field that you're trying to fit. And you can also work with residuals to make it a little bit more efficient so that you don't have to call a forward solver. So if your PDE is linear, then you can work out the Radon-Nikodym derivative, and it turns out that the posterior will also be a Gaussian measure over the same space. And then there's also some fringe cases where you can construct Gaussian processes which a priori obey the PDE, but these are quite limited. And if your PDE is nonlinear, then your posterior is not going to be Gaussian, so you have a difficult time characterizing it and sampling from it. There's also a number of discretization first approaches. So kernel ridge regression, Gaussian process regression, and solving these Bayesian inverse problems in the sense of Andrew Stewart approach, they formulate this problem in your function space, and then you discretize everything afterwards. And then there's other methods out there which sort of discretize everything first, and then you derive the objective or the posterior using the usual form of Bayes' rule. So some examples would be numerical Gaussian processes, which build covariance kernels from PDE solvers. PINNs take this type of approach. Bayesian PINNs also do this, where you define the posterior over the network weights. And then there's Gaussian processes for nonlinear PDEs, which put the PDE residuals into the likelihood. And there's many, many more, too much to go over. So the issues with these existing non-parametric methods is that MCMC sampling is slow. Because you put your physics into the likelihood, every single time you want to sample from this posterior, you have to solve the PDE so that you can evaluate the likelihood. So if you have an expensive forward model, this will be quite inefficient to do. This approach also fails to account for model form error, in that whenever you place the physics into the likelihood, this is explicitly in assumption that the model you have is correct, it's perfect. It completely determines your data. And so what this means is that if you've selected a model which has some error to it, your uncertainty in the solution to the inverse problem is going to adjust unnaturally, and you're not going to be aware of this. And so your posterior may actually collapse to the wrong answer. In the limit of infinite data, the posterior wants to collapse to the maximum likelihood estimate. So if your likelihood is coming from a model which is wrong, then your solution to the inverse problem is going to go to the wrong answer. And there's also some theoretical issues, which I won't get into today, but your posterior is well defined only if your measurement operator, the domain of your measurement operator, has full measure under your prior. So again, your measurement operator is coming from the physics. So its domain is sort of the solution space of the PDE. So you can think about if you are trying to solve an inverse problem involving fluid flow, then you can't really say for sure that you've picked the correct prior, because you don't know the solution space of Navier-Stokes equations. And then also these Gaussian process kernels coming from PDEs are not easily understood, namely that the reproducing kernel Hilbert space of your kernel that you're defining from the PDE is probably hard to derive, and this determines many important things in the actual regression. So things like your sample path regularity and the space that your map estimate will live in depend on the reproducing kernel Hilbert space of your prior kernel. It's also a bit, to me, at least, philosophically unsatisfying to put physics into the likelihood. Because whenever we are studying an inverse problem involving, let's say, the thermal conductivity, we know ahead of time that the temperature should satisfy the heat equation. This should be our prior knowledge. So we want a way where we can put this as prior knowledge. And so all of these issues are sort of coming from the fact that we are putting the physics into the likelihood under all of the standard methods. So the motivation behind IFT is that we wanted to develop a new non-parametric Bayesian method for solving severely ill-posed inverse problems in a way that allows us to encode nonlinear PDEs as prior knowledge. You can incorporate multiple sources of uncertainty, including model form error. You want to fuse together multiple measurement modalities so that it generalizes well. And you want to be able to balance your contributions from the data and the physics automatically. And whenever we looked at these things, what we uncovered is that to build priors from physics and make a Bayesian method which works in this sort of way, we're going to need non-Gaussian probability measures in Banach spaces. And that's where that's what led us to IFT as the language to do this. So we've been taking this method IFT, and whenever we add physics into the priors, we like to refer to it as physics-informed information field theory. So we take our inspiration from physics, where we define everything using the language of path integrals, which were made famous by Feynman, of course, But actually, this idea predates Feynman. It goes back all the way to the early 1900s with John Percy Daniell, who first sort of proposed this integral and function space idea. So how physicists view path integrals is we take an infinite limit of finite dimensional integrals, and this is how we can integrate over function space. So these appear all the time in statistical physics and, of course, quantum field theory. I think the best resource to read about these for mathematicians is the book by Glim and Jaff down there. So they went and they tried their best to make path integrals rigorous. So the issues that the mathematicians take with path integrals is that, of course, they're not entirely well defined because we know that the Lebesgue measure cannot exist in infinite dimensions. And so what this means is that most path integrals diverge. But then the argument that physicists give back to them is that ratios of path integrals can give you reasonable answers. And then we take this idea of path integral and we develop all of the theory without ever needing to actually evaluate them. And then in the end, we discretize everything where it all becomes well-defined again. So we try to avoid this theoretical issue that the path integral doesn't actually work out. And I'm not interested in proving the existence of path integrals because it's actually related to a Millennium Prize problem. So this goes, this is above my pay grade. So what Inchlin's group was developing whenever they developed IFT about 10 or so years ago was they were using only Gaussians. So IFT is just Bayesian statistics over fields using these path integrals. And how we define all of our probability measures is with these formal Lebesgue densities, which take this Boltzmann-like distribution. And we define them over the space of field configurations. So what goes on the inside of this Boltzmann distribution is some functional that you want to minimize. And I refer to this as an information potential so that it matches the rest of what our field is doing in traditional inverse problems. But the physicists who work on IFT like to call it an information Hamiltonian. And then the normalization constant is called the partition function, which is where the path integral shows up. And then what was done in classical IFT was everything was working with Gaussian measures. So if you have a Gaussian measure on a Hilbert space, you can represent it as an IFT prior using this form, where your formal Lebesgue density sort of resembles the PDF of a multivariate Gaussian distribution. But now you've replaced your covariance matrix with the covariance operator, and you use the correct inner product, so the L2 inner product. And these are often actually well-defined as abstract Wiener measures, if you know what these are. And I say often here because you need your covariance operator to be trace class in order to get an actual Gaussian measure.
Alex, can I ask a question? So in this case, Z, the normalization constant is the determinant of C.
Yes.
I see.
So this is it's just the normalization constant of the Gaussian measure, which you can work out. It's related to like the Fredholm determinant of the operator.
So the path integral can be easily computed, obviously, and that's the answer.
Yeah, the path integral can be computed only if it is, well, not only if, but the majority of the time you can only compute the path integral if it's a Gaussian form.
Great, thanks.
All right, so we took these ideas coming from IFT to define priors involving physics. So in classical IFT, you're working with Gaussian measures. So your prior encodes field regularity constraints, smoothness, or symmetries. And what we're interested in is defining IFT priors which work with conservation laws, differential equations, or field energy. So how we do this is we want to formally define a prior probability measure over fields such that fields which satisfy the physics are given higher probability. And we also want to be able to adjust our belief in the physics so that we can account for model form error and enforce the physics as a soft constraint. So how this works is you start with some PDE with boundary conditions, and then you turn it into an optimization problem. So you can do this either with a variational principle, or maybe you take the integrated square residual. You just want a potential function that works in a way where if a field U minimizes this objective function, it solves the PDE. And then we take this optimization problem and we stick it inside the Boltzmann distribution to define what we call a physics-informed prior. And we include this extra parameter beta in front of it, which controls our trust in the physics. And I will spend a great deal of time talking about how this beta.
So Alex, I have a question here. So what happens if you don't have you cannot write the integral, let's say in the Navier-Stokes equations, you cannot write that. Is it okay to do like a Galerkin type multiply by some functions and try a variational form and write that?
But I mean, so first, if you don't have like a variational principle, then you can always start with the integrated square residual, which of course doesn't behave as well. The only criteria to define this prior is that you can represent your physics as some sort of optimization problem that you're looking to minimize.
Okay, how do you do that in Navier-Stokes?
So for Navier-Stokes, we just take the Navier-Stokes equation and we just write the integrated square residual. So for each dimension, you have the integrated square residual for each dimension, and then each of those integrals gets its own parameter beta.
Okay, so you work with residuals, not with...
Yes.
Okay. Thanks.
Anyways, so our prior is defined in such a way where if a field solves your optimization problem, so it minimizes this variational form, then it's given this assigned maximum probability. So if we can imagine how this prior would look like in function space, the first observation is that our prior is concentrated around PDE solutions. The second observation to make is that beta will actually control the spread of the prior, so it diffuses it. So if you select beta equal to 0, then you have a flat prior in function space, and you consider all fields to be equally likely. And as you send beta to infinity, the prior starts to collapse around the unique solution to the PDE that you have. And we're interested in this case where you're somewhere in between, where you have a model that is pretty good, but it has some error to it. So you should consider more fields than just the one that your model is representing, because you have some error in your model. So as your ground truth physics that you've selected get closer to as your ground truth physics get closer to the energy function that you've selected, then you should assign a larger value of beta or a higher amount of trust in your physics. And then the idea behind our approach is that if you treat beta as a parameter that can be trained, then the method will automatically do this for you, and it will assign belief to your physics that you selected. So for the likelihood, we describe the data using a greatly simplified measurement operator compared to the standard approach, where mostly you only work with point measurements or maybe a spatial averaged measurement. So there are no physics in our likelihood. It's just, I observe the temperature. This is the data that I have. And then we turn this into a likelihood potential using the same language of IFT. So if you have point measurements with Gaussian noise, then you would just have the usual square loss. And then we write our likelihood also in this type of form so that things combine together nicely. And then we formally apply Bayes' rule to give us the posterior distribution. So we take the prior and we combine it with the likelihood, and we end up with a posterior that looks like this. So beta, you can see, is sort of like a learning rate, which balances our contribution from the physics and the data. And because we've derived the posterior distribution in infinite dimensions, then discretization is up to the user. You can pick your favorite method when sampling from this. So let's go through a rigorous example where I'm going to argue that if you're trying to solve the Poisson equation, then the correct prior is the Brownian bridge. So I study the Poisson equation with Dirichlet boundary conditions. And so you can turn this into an optimization problem using Dirichlet's principle, which is the variational form of this Poisson equation here. So if you minimize this energy functional, then it gives you the unique solution to the Poisson equation. So we take this energy functional E and we put it into our IFT prior in the type of way like this. And then we can actually prove that for this equation, the IFT prior can be viewed rigorously as a Gaussian measure. So it's a well-defined object. So how you can show this is first, you could connect Dirichlet's principle to a kernel method. So you can actually identify a hidden covariance form in Dirichlet's principle. So you find that the same energy functional just looks like this squared reproducing kernel Hilbert space norm, where you're taking the difference between U, which is the input to the energy function, and the unique solution to the Poisson equation. And then the norm you work with is the norm in the reproducing kernel Hilbert space, which takes this kernel. Here I'm using multi-index notation because it gets very, very long if you have more than one dimension. And this kernel is exactly the Green's function of the Poisson equation with Dirichlet boundary conditions. And it's also the covariance kernel of the unit Brownian bridge. And how you can prove this is you just take the energy function appearing in Dirichlet's principle and you complete the square. And then you apply Mercer's theorem to get a nice representation of the norm. So the Mercer representation of the objective for the Poisson equation gives us this type of form. And this reminder, this goes into our IFT prior. So here C is the integral operator with kernel K. So this is the inverse of the Green's function of the Poisson equation. So our IFT prior looks like this, which again, this covariance operator here is the covariance operator of the Brownian bridge. So our IFT prior for the Poisson equation is just a shifted Brownian bridge prior, where we center the prior at the unique solution to the Poisson equation. So this is a nice theoretical justification of what we are doing with these priors, that they are actually centered at the unique solution to the PDE, and somehow the regularity of the prior is related to the PDE because the covariance operator of this prior turns out to be the Green's function of the PDE that we started with. And so from this form, we can see exactly how beta is controlling the prior. So we have a Gaussian measure on Hilbert space where our covariance operator is the inverse of beta times the Brownian bridge operator. So again, our prior is centered at unique PDE solutions, and the variance will decrease as beta gets larger because the covariance operator has the inverse of beta. So if you send beta to infinity, then it's actually, the prior will actually collapse to the unique solution to the Poisson equation. And as you pick a lower value of beta, the prior diffuses and you consider more and more fields. So another fact about this is that the Cameron-Martin space of this prior is sort of the ideal case, namely that if you were to do regression with this Brownian bridge, then the resulting posterior mean function will live in the solution space of the Poisson equation, which is sort of the best case scenario that you can have. So now that we've showed this, let's talk about how we can solve inverse problems under our IFT approach. So if we assume that our PDE has some unknown parameters or unknown fields, lambda, then of course they show up in your potential function. So then you place a prior over your hyperparameters, and I use this type of form so that all the notation looks nice. And if lambda is a field, then you can apply the standard approach and assign a Gaussian measure to these unknown fields. And then we now take our physics-informed prior and we just condition it on the hyperparameters. So it has the same form, but now the partition function, which is the normalization constant of the prior, will depend on your parameters, which creates some issues that we'll get into. So your partition function needs to be evaluated at different values of lambda. So if you're trying to solve the inverse problem where you are identifying lambda, you have to start by writing the joint. The reason for this is because under IFT, we treat learning the solution to the PDE as part of the inverse problem because we assume that we have some amount of error in the model. So you write down the joint posterior. So whenever you write down the joint, the normalization constant of the prior will show up in the joint, and this z, again, is a path integral, which in most cases you cannot evaluate. And you can't just write that this joint is proportional to something because the normalization constant can't be dropped. However, we can make sense of this object by studying the marginals. So you take another path integral where you integrate out the solution to the PDE, and you just say, the only object that I care about are these hyperparameters or hyperfields, which show up in the physics. So we derive a nice analytical form of this marginal distribution. So we define what the expectation of a field is. So if you take some functional and you want to find its expectation over an IFT prior, then you just write down this path integral. And then given this definition, we find an explicit expression for the marginal as these expectations. So we start with the IFT prior and IFT posterior, where now we work with the joint. And then you take the gradient of the log of the marginal. It is equal to the difference between these two expectations, where the first expectation is over the conditional prior, and the second expectation is over the posterior coming from the forward problem. And what goes inside these expectations is just the derivative of your potential function. And what matters here is that because all of these expectations are conditional on the value of lambda, that lambda is actually fixed during these expectations. And then you also have a contribution from the prior that you pick on lambda.
So Alex, this is like a score function for lambda, right?
Yeah, it's similar, yes.
On the left-hand side.
Yeah. So it just turned out that we could only find an expression like this if we took the gradient.
Yeah.
So yeah, how we're working with this is now we have an expression for the gradient of the log as a bunch of expectations. So we can build sampling averages of these expectations and then use this gradient to push it forward through stochastic gradient Langevin dynamics, because SGLD generates samples from probability distributions using their gradients. And now we have a nice analytical form of this gradient of the marginal, where everything is an expectation. And whenever we take sampling averages, we don't have to evaluate any path integrals. So we've removed the need to ever work with these path integrals. And if you're interested in more of the theory, then you can actually justify these sort of formal manipulations of path integrals using something called a Wick expansion. Of course, it doesn't prove that the path integral exists and is well defined. A Wick expansion just proves that if you accept the path integral to be true, then your formal manipulations are justified. And that's the philosophy that we work under.
But just so that everybody can understand what you're saying is that basically this is a computable form if you use Langevin dynamics.
Yes, this is form is computable.
Like a HMC, but Langevin dynamics, yeah.
Yes. Or you could use Hamiltonian Monte Carlo, but
that's what I saw. Maybe HMC, yeah.
Yes. All right, so I'll talk about how we actually work with this in practice, how we're sampling from these objects. So again, we derive everything in the infinite dimensional setting, and then at the end, you parameterize so that you can generate samples. And you can parameterize the field in any way that you want. So we work with truncated basis functions or a neural network. And then your physics-informed prior conditional on the parameters now becomes a physics-informed prior on the parameters of your field representation, so your basis functions or your parameters of your neural network. And then the same thing happens to your likelihood, where now your likelihood is depending on the parameters of your basis. And then you write down the joint posterior over all the parameters. So if you're solving the forward problem, so you know what all of the hyperparameters of your PDE are, then this z, the partition function, is actually a constant. So you can drop it and you can sample this you can sample this posterior, which would just be a posterior over theta, your basis function parameters. So you can sample it using vanilla SGLD, Hamiltonian Monte Carlo. We've also developed variational inference approach for solving this problem as well. And then likewise, if you are trying to solve the inverse problem, so I have a typo here, this should be the marginal over lambda, not theta, then you can sample from this object. And we have from the previous slide an analytical expression for the gradient, the log of the gradient of this. So to sample from this marginal distribution, SGLD requires an unbiased estimate of the log of this. And from computations, we have this form. So now I've taken that same form where we had all of those expectations, and I've plugged in my field parameterization. So now the expectations are taken over theta. So this is a finite dimensional object that you're taking the expectation of. So the expectation goes over your physics-informed prior, which now gives you parameters of your basis function. And then the other expectation is coming from the posterior distribution of the forward problem, where lambda is fixed. So we do this iteratively. So you get prior and posterior field samples with lambda fixed. So from there, you can just sample the distribution where you assume that you know lambda. And then now we want to push lambda forward once. So you take those prior and posterior field samples and you build a sampling average approximation of these expectations which show up. And then you use another step of SGLD to push lambda forward. Now you have a new value of lambda that you generate field prior and posterior samples over, and then you use this to push forward lambda again. So we work with a nested scheme, and this works in a way where we never actually have to evaluate any path integrals. And this comes at the cost of working with a nested sampling algorithm, which of course has some computational deficiencies. So let's talk about the forward sampler, so how we're actually generating samples from the field prior and posterior. So we also do this with SGLD. Remind you that our physics-informed prior over the parameters of your basis functions has this type of form. So if you write down the log, it's equal to up to a normalization constant, your minus beta times your potential function. And then we invoke importance sampling. So we take this integral which shows up in the potential function and we write it as an expectation using importance sampling. We are just sampling collocation points in the domain using some distribution. And so whenever we do it this way, we have no forward solves are needed. You're just evaluating your potential function, the integrand of the potential function, and then taking the average. Now, this is extremely scalable because this will actually converge. We can prove that when you sample in this way, the posterior will converge to the true posterior distribution, even when m equals to 1. So every single time you generate a new set of basis function parameters, you only ever need to evaluate the integrand at a single point, which is like the residual of the PDE. So you only have to evaluate the residual at a single point, and you have convergence. And then we sample this using SGLD or also Hamiltonian Monte Carlo with energy conserving subsampling, because we are doing a subsampling scheme, a mini batch scheme, so you can't just sample with vanilla Hamiltonian Monte Carlo. You have to ensure that it converges. So for this, you need to add this additional energy conserving step. Now let's talk about the Gaussian case, and we can prove that we are doing the right thing. So if we have a Gaussian measure that we want to sample from, then you can pick any orthonormal basis in L2 and consider finite dimensional subspaces, which are spanned by that basis truncated at some points. So if you pick piecewise constant functions, then this is equivalent to taking test points like you would when you're doing Gaussian process regression. And then we define the restriction of the covariance operator to this finite dimensional space to be this sigma f. And sigma f is now a finite dimensional operator, so you can represent it as a matrix. And so now this is just the covariance matrix of a unique finite dimensional Gaussian measure, which is described by the Lebesgue measure in a finite number of dimensions. So this sort of restriction of our IFT prior is well-defined in finite dimensions. And then our finite dimensional representation has the correct limiting behavior in that our truncated basis completely determines the finite dimensional space where our prior is well-defined. And then if we refine this mesh further by taking the same basis and we add more orthonormal basis functions, this does not change the behavior of the prior on the larger space when restricted to the smaller space. So what this tells us is that in applications, there is some cutoff point where adding more basis functions does not benefit you, because it doesn't actually change. I mean, it changes the behavior of your prior, but sort of you can make it go to an infinitesimal amount. And then we can also prove that our IFT prior converges to the correct Gaussian measure. So if you start with an orthonormal basis and you start writing these finite dimensional IFT priors, then you can prove that as you send the number of basis functions to infinity, the finite dimensional prior converges to the original Gaussian measure that you started with. And how you prove this is you use characteristic functions. So you write down the characteristic function of your finite dimensional prior, and you prove that your characteristic function converges to the characteristic function of the Gaussian prior that you're after. And then, of course, convergence in characteristic functions implies convergence to in measure. Now, we also need to go over infinite trace kernels. So we can also prove that the finite dimensional IFT prior in the Gaussian form case converges to the correct stochastic process. So you won't get a Gaussian measure, you will just get some stochastic process. This is relevant when you are dealing with the Poisson equation in more than one dimension, because the covariance kernel of the Poisson equation beyond one dimension has infinite trace. So it can't define a Gaussian measure, but it can define something known as Levy-White noise, which is defined over the space, the dual of the Schwarz space. And we have convergence to the correct stochastic process. Now I'll get into connections to other methods. So I'll connect IFT to deep Ritz PINNs and so on. So deep Ritz is essentially just doing PINNs, but where your loss function is a variational form of a PDE. So if you take deep Ritz for the Poisson equation and we take Dirichlet's principle, previously I showed you that this energy function can just be written as a kernel method where C and K are coming from the Brownian bridge. So C and K are describing the Green's function of the Poisson equation, which is the same operator that defines the Brownian bridge. And then I also showed that the IFT prior for this case is just a shifted Brownian bridge. And so we can make the following connection between this deep Ritz method and Gaussian process regression for this case. So we show that if you use the same training data and you're trying to solve the Poisson equation and you represent some target function, then if you select this magic relationship between the learning rate of deep Ritz and the noise, and now we also have this parameter beta, which shows up from our prior, then the posterior mean function resulting from doing the IFT lines up perfectly with the solution to this physics-informed optimization problem, which is described by deep Ritz. And this result follows from the connection between Gaussian process regression and reproducing kernel Hilbert spaces. So we can also show that PINNs can be viewed as a map estimate of IFT. So if you start with a PDE and you turn it into a residual, and then you parameterize your field with a neural network, then our IFT posterior looks like this, where now our posterior is over the parameters of the neural network. If you take the map estimates of this IFT posterior, then what you recover is exactly a physics-informed loss function, and it's over the parameters of a neural network. And then the last method to compare this to is Bayesian PINNs, where we have this result where IFT and Bayesian PINNs do not agree. We don't get the same posterior. So in Bayesian PINNs, you parameterize the field with a neural network where you assign a Gaussian prior over the weights. And then the physics enter the likelihood. So you assume that you are observing the PDE residuals as some predetermined collocation points. And then you assume that the residuals are some random variables which are normally distributed. And then the Bayesian PINNs posterior is derived on the assumption that your PDE residuals vanish. So if we compare the Bayesian PINNs posterior and the IFT posterior, we see that the first two lines are roughly the same. If we are subsampling the IFT integral at the same collocation points as what you're doing for Bayesian PINNs. And the difference shows up in this last line, where Bayesian PINNs has this additional regularizer coming from your prior over the network weights. And we have this partition function, which comes from our IFT prior. So they don't agree. And if you want to see direct comparisons in numerical experiments, then I'll point you to the work of Kairi Hao, who is a former student of our group who graduated last year and now has a job somewhere else. So you can go read his papers to see some numerical experiments where we compare the two methods. So IFT, it captures model form error. This is, now I'll get into some numerical experiments. Reminds you that the prior looks like this, where as beta grows, you have less variance in the prior. And for this reason, we view IFT as treating the physics as a soft constraint, where the map estimate of beta, if you were to train beta, is actually going to be sensitive to error in your physics. So we look at the map estimate of beta here. And the idea is that if we train beta, it's going to allow the IFT posterior to also learn under model form error. So it will recognize if you select the incorrect physics, and it's going to adjust accordingly. So we see this in some synthetic examples where you can control exactly how much error you have in your PDE. And what we find is that as your chosen model gets closer to the ground truth physics, which generated the data, the posterior of beta goes to a larger value, which means that we are collapsing the variance of the prior and also the variance of the posterior, because we have larger belief that the model we picked is correct. So we should consider only fields which are very close to solving the physics. And we can also show an explicit theoretical example where if we start with a PDE which gives us a Gaussian prior, then we can analytically derive the gradient of the map estimate of beta. And then if you take some limiting procedure, then what we find is that the map estimate of beta is proportional to this norm, where we are measuring the distance between the ground truth field which generated your data and the unique solution to the PDE that you've selected. So if you pick the exact perfect physics, then this distance is 0 and beta goes to infinity. And as your physics gets worse and worse, the solution to your physics will grow further away from the ground truth which generated your data, and beta goes to a smaller value, which means that you put less trust in the model you have and you consider a larger range of physical fields. So we applied this concept to diesel combustion engine modeling, where we work together with Cummins, and they ask us to build a nice empirical model of this intake manifold subsystem, which is where the fuel is injected into the engine. How this model works is we have something called EGR flow, which is exhaust gas recirculation, where the part of the emission is recycled back into the engine. And so we have this model which has exhaust gas recirculation, and we want to model the temperature and pressure dynamics of the intake manifold. So the dynamics that we have come in the form of a mean value engine model, which was developed by Hendricks in the 90s, where the equation for the temperature looks like this, which is just the ideal gas law plus heat transfer equation. And then we have some heat transfer effects, and this is what we want to calibrate. And we also have an equation for the pressure. Now, it is known that the model performance of this model will degrade as you actually have exhaust gas recirculation. The reason for this is that Hendricks wrote this model before exhaust gas recirculation was even a concept. So it was built for engines in the 90s where they weren't using this idea. So we're applying this model, which was derived without exhaust gas recirculation, to the case where we have data which has exhaust gas recirculation. So the inverse problem that we have at hand is we want to calibrate the heat transfer effects. So we don't know the heat transfer coefficient, the emissivity, or the temperature of the actual intake manifold itself. And we simultaneously want to reconstruct the temperature inside the intake manifold and also the pressure so that we can do some uncertainty propagation to the engine cylinders. So if you look at how IFT solves this problem, is that if we feed the method a data set which doesn't have EGR flow, we get a nice, relatively large value of beta for the map estimate, and we get some very clear shapes for the posterior over these parameters. Now, if we give the model that has EGR flow, so we know that the model performance should degrade, then beta, the map estimate of beta goes to a much smaller value, and it's telling us that this model has some error, you need to change something about it. And also the posterior distribution over the other parameters spreads out. And if we directly compare the posteriors that we get, we find that for the same model, if we give it a data set with EGR or without EGR, the posteriors look completely different. So when we have EGR, which is the case where we know that the model should be wrong, we get a very flat posterior distribution. This is because the IFT posterior has detected that your model has error. So it responds by not being overconfident in the prediction of your model parameters. It says, how could I possibly calibrate these model parameters if the model doesn't generate this data? So a quick summary of everything is that IFT is just a path integral framework for solving infinite dimensional inverse problems with physical knowledge. So I talked about why we even care to do this, going through some of the challenges of the standard approaches. And then we derived physics-informed priors using the language of IFT. And then I showed some results which prove, at least in certain cases, that we are doing the correct thing. And then I established connections to other methods, mainly that at least I view that IFT can be viewed as a Bayesian interpretation of physics-informed neural networks. And then IFT can also capture model form error. So when you would want to apply this is if you're solving severely ill-posed inverse problems. So maybe you're missing boundary conditions, or you don't have enough measurements to determine all the parameters, or you have some unobserved or partially observed states, then including any amount of physics in your Bayesian inverse problem will help improve the results of your method. And maybe you're not entirely confident about the physics. So you're working in regimes where the physics are not completely known, or maybe you've built some empirical models and you want to test the amount of error between them to compare. And this works because IFT treats the physics as a soft constraint, and it's automatically balancing your contributions from the physics and data for you. And then other scientific machine learning methods are limiting cases of IFT. So perhaps some of the theory, which may be easier to derive in the path integral setting, can trickle down to the other methods. So that's everything that I have for you today. So I'd like to thank you again for inviting me to speak. And these are the papers that I went over today. So thank you.
Thank you so much, Alex, for that nice presentation. Do you have any questions from the audience?
Yeah, actually, I'm hearing an echo.
Oh,
So I have a couple of questions.
Maybe the other people in the room should
Yeah,
mute.
can you mute the microphones? Okay, so there's still echo. I will just try it because I'm gonna mute my.
Hussein, can you mute? Hussein, can you mute? Can Hussein mute?
I have a philosophical question, and it gets a bit technical
I muted
fast,
him.
and that is about your beta that you called a belief. And the way that you're using defining and using it, it seems more like to be a temperature, because it seems to be bounded below by 0 and not bounded above. If it were a belief, it should be bounded above it, at least if we take this interpretation of what is a belief as in probability. So beta should be a probability between 0 and 1, or between whatever is your definition of that. Whereas a temperature is not really bounded, right? So that's a bit philosophical now, but it would also have some implications on your prior for beta. So my question is, what is your prior on beta?
So for the most part, we work with Jeffrey's prior for beta because, I mean, if any given problem, you don't really know what beta should be or even the scale of it because, I mean, it depends completely on the parameterization you're using, the physics that you have, your data. It will depend on all of these things. So if you use Jeffrey's prior, it's invariant to scale, and it's sort of the most uninformative prior that we can use. The reason that we allow beta to go to infinity is that we want to allow for this case where the posterior distribution collapses to the solution to the PDE. So this is the case if you've picked the exact perfect model, because if you have the perfect model, then you shouldn't consider anything else besides the solution to your model. And you're right that, I mean, it's exactly the inverse temperature that appears in the Boltzmann distribution.
Wouldn't it at some point then be possible for the physics to beat the data, in a sense, to override the data?
Yeah, I guess so. But it wants to find a nice, I mean, the posterior over beta wants to find a nice balance because it needs to also respect your data as well. So I mean, I suspect that the optimal value of beta is probably the inverse of the noise in your data, but I'm not 100% sure on this. The only case where we can find the unique map estimate is whenever you work with a PDE that gives you a Gaussian IFT prior.
Okay, thank you, Alex.
Alex, I have a question on the beta as a reflection of the representative of the model uncertainty. In the Cummins engine example, we also work with Cummins on the same engine. But anyways, so what happens? And your results are very clear. But just I was wondering if I reparameterize my network and I have a different hyperparameters in my network, then I have epistemic uncertainty that comes from that. So that's also included that U minus U naught difference. So it will not
Yes.
just reflect the model uncertainty, it will reflect maybe a total uncertainty, right? You assume that you basically did not rediscretize the system, you not reparameterize the system under the same conditions, then this amounts to model uncertainty only.
Yeah, so I forgot to mention, but in this map estimate, I put the bars over these because these are the projection of your ground truth and the solution to the PDE onto the subspace defined by your parameterization.
Right. So the parameterization is there.
Yeah, so beta depends also on the parameterization that you
Yeah,
pick.
exactly. Exactly. Yeah. But it's good to show. It's a very nice measure too. And we know that, as I said, this in you use that beta in posterior tempering. If you're because sometimes you're not sure about your posterior, so you're basically doing something similar to focus or make more uniform the posterior. So that's a trick that is used in posterior calibration.
Yeah, of course.
Yeah.
Great. Do we have any other questions from the
Maybe
audience?
Z-Way. I don't know if Z-Way has any questions. Z-Way, go.
I don't see him. I'm not sure if he's here. I've just checked the participants. Since I do not see Jiwei, so maybe does anybody else have questions? Ask questions?
Yeah, maybe I have one more question or comment. Is there you showed some equivalences, one being the equivalence or the analogy, whatever to call it, between kernel regression methods and Gaussian processes, and another one was between deep Ritz and this IFT approach. And from my understanding, both were based on an assumption of Hilbert spaces, right?
Yes, yeah.
And you might be interested in this. There's a generalization of the representative theorem to Banach spaces.
Okay, can you email it to me?
Of course. So from a guy Michael Unser in Switzerland.
Yeah, that sounds interesting for sure.
So actually, I didn't quite understand where you were really using Banach spaces, because in the beginning you were mentioning, okay, we're talking about Banach spaces, but then most of the time you were using Hilbert spaces, right, or Hilbert space properties.
Yeah, so I restrict to Hilbert spaces because we're solving PDEs where we know that their solutions are mostly in subless spaces. And the other reason is that Gaussian measures on Hilbert spaces are much easier to describe in a talk than on a Banach space. Because when you put on a Banach space, you have to define the cylinder sets and what they are. And it's very complicated. But on the Hilbert space, you can just work with everything in L2. Where the definition of a Gaussian measure on L2 is much easier to write down than on a Banach space.
Maybe
Yes,
some
there's
future
excellent
directions.
talk. Alex, there was excellent talk. It's very useful. One thing I mentioned before is this connection with functional priors. I don't know if you look into it, because you point out the difference between Bayesian, which I remember from last time that we talked, but the connection, I think there's still a connection with functional priors.
Yes, of course. So what we're doing is essentially a functional prior, but we aren't we're not looking for it. Essentially, we are assuming that it has a certain form. So we've assumed that the functional prior looks a specific way, and then we work with that assumption rather than training the functional prior ahead of time.
Yeah, because you can do the E of U can be computed both from, you can use historical data and you can use the physics, right? So you can use EU to compute a residual of those. So then it would look like a functional prior. It doesn't have the Gen AI part that we use.
Yeah, that would be certainly very interesting. Yeah, something that I've thought a lot about but haven't quite gotten to is building empirical models and then putting them into our prior and seeing what happens with beta.
Yeah. Also, is any code available from these papers?
Yes, so we have code from the first one up there. And then the second ones are all theory. I don't have any code.
Is that on your GitHub? Where is the code?
Yeah, they're on our GitHub for the predictive science lab. But the code for the first one is 2 years old, and we do have updated code. I just haven't put it on GitHub yet because I need to.
We may get back to you because we're interested in using it in some applications.
Yeah, so the first code is in C++, but now we do have code in JAX. I just haven't put it up yet because I'm finishing up a paper hopefully by the end of August because my co-author is leaving for a job. So we need to finish by August, and then I'll have JAX code for this method.
Sure.
Okay. Do you have any other questions?
If I may ask another one, or too late? So Alex, your sampling procedure reminded me a lot of nested sampling. But what's the relationship to nested sampling of this sampling approach?
Well, our sampling approach is nested sampling. It's just a very specialized for
Okay.
nested sampling because we have this issue with the path integrals that show up in the posterior. So we need to nested sample in a certain way to avoid having to evaluate the path integrals.
There's basically nested sampling, but you're using the gradient to move the walkers.
Yeah, we nested sampling, but with SGLD.
Yeah.
And technically, you could also use a variant of Hamiltonian Monte Carlo to do it, but it is much, much slower.
Okay, great. Thank you so much, Alex. Thank you so much, everyone, for your questions. And thank you so much, Alex, for your time. This was a really nice presentation. And I think that we're already like almost like 20 minutes past it. So maybe it's a good time to close the seminar. Thank you everyone for your time, and until next week.
Thank you.